Okay, well, hi everyone, welcome to this session. So it's time, so let's start the session. Uh, uh, Doctor, I think you can hear us, right?
Yeah, I'm here.
Okay, thank you. So, yeah, I will first welcome Dr. to give us a lecture. Dr. Cao is a Senior Schmidt Science Fellow, a lifetime fellowship by Schmidt Science, and he was mentored by SF Academic Council's founding chair, Professor Burnett. And he pursued his independent research version of integrated carbon capture and utilization at MIT and built independent collaboration with researchers across three continents. Dr. has been named an active fellow at MIT Climate and Sustainability Consortium Impact Fellow, a Carbon Removal Justice Fellow, and a German Chancellor Fellow by the Humboldt Foundation. So let's welcome Dr. Cao to give us a keynote lecture on the topic of surface and structure engineering for decarbonized future. Welcome.
All right, thanks so much for the introduction. Let me go ahead and share my screen. So you guys can see the screen, right?
Yes, please
Okay.
go ahead.
All right. So it's a great honor to be back to give the talk virtually. I know it's happening in Xi'an where I get my undergrad degree, so it's really excited to have the opportunity. And today I would like to talk about surface structure engineering for a decarbonized future. I will choose several of my past work and share with you some of the considerations behind. So first off, I would like to mention, so the talk is divided into the three sections. I will firstly just briefly introduce my personal background, and then we'll talk about one of my earlier work on reactor engineering for CO2 conversion into for fuel production. And we also talk about some of the recent work on air filter design for particular matter capture. For both of work shown here, we focus on the device and structure engineering. So first of all, I would like to say, actually, I got a huge, great opportunity to conduct my first project with Professor Bai during my undergrad study in China. That's over 10 years ago. Time flies. So after that, I got opportunity to get my master's degree from McGill University in materials engineering, and also my PhD degree from mechanical engineering from Cornell University, and most recently also at MIT as a Climate and Sustainability Consortium Fellow, and then later as a Schmidt Science Fellow, and most recently as active fellow to focus on entrepreneurship side of things. So if I were to use three keywords to define my background, I think the first one would be a multidisciplinary engineer, as showing from my multiple degrees from MIT, McGill, Cornell, and also Xi'an University. I also have a huge focus on human dimension technology. So when we design technologies, for example, in climate sustainability, recently I got a grant on climate justice to focus on a design aspect on how we can use the technology to benefit the communities, to maximize co-benefits. And also I have showing multifaceted broader impact in my past record. That include entrepreneurship, as showing in a Carbon Express final here, and also Forbes 30 active fellow. This is all related to entrepreneurship. And then I also get opportunity to participate in policy making as one of the UN Technical Working Group member on energy transitions to co-author energy roadmaps. I also have a huge focus on service form narratives to build a better academia. So these are my recent two fellowships. One is the Schmidt Science Fellowship as one of the 29 fellows selected by Eric and Winnie Schmidt to focus on interdisciplinary science, and also was one of the 46 fellows in active fellowship program in the U.S. to focus on how we can translate learnings from the laboratory to do the science in the real world. And one of the highlights is I got into the Forbes 30 for North America for my reactor engineering work for CO2 capture and conversion. So firstly, I wanted to talk about the first work, which is solar-driven reactor engineering for CO2 conversion. I will focus on how to build a structure and also the surface components inside the reactor for this application. So firstly, let's just think about what is the scientific problem I try to solve. So instead of thinking about CO2 conversion, let's first focus on, let's say, if you have an open pond and you want to maximize algae growth inside the pond. So in order for algae to grow, you need to have natural photosynthesis. And in order to have the maximized natural photosynthesis, you need to have the light and also the fluids, which is the CO2 in this case, to be delivered to all algae in open pond system. Let's imagine you have very dense culture of the algae. Due to the shading effect of the algae themselves, only the top layer of the algae on the surface to the water will get access to light irradiation, and where there will be overexposure of light. And if you move further down from the surface to the bottom, due to the shading, as I already explained, by the algae themselves, the bottom layer of the algae solution, they don't get access to sufficient light irradiation. So in that place, you have the underexposure. So as you can see from the open pond analogy, there is a non-uniformity of light distribution. And also you can imagine the fluids, which is the CO2 distribution, is also non-uniform. And that will lead to a huge challenge in enabling the increase of natural photosynthesis rate. And similarly, if you think about many of the climate sustainability problems, let's use artificial photosynthesis as an example, where you put CO2 and other reactants into the reactor, and then if the reaction is also driven by solar, and there's a similar challenge in delivering the light and also the fluids, which is the reactant flow, to the desired location, similar to the algae. Here, instead of algae, is actually the catalyst surface where the reaction happens. So I ended up using a tool called optofluidics, which is a combination of optics and microfluidics to enable concurrent delivery of light and fluids to the desired location with the catalyst surface. And so let's look at what, how photocatalysis is being done right now and what are the problems. If you remember the open pond analogy, if you look at the system for the photoreactor here, you have the UV light to provide irradiation for the catalyst materials, and the catalyst materials are packed in these different configurations, and whatever configuration they have, if you don't do any of the light guiding, if you have similar problem, which is the top surface of the catalyst will get overexposure of the UV light. And if you move further down, due to the shading effect of the catalyst material themselves, they don't get access to light. And without light irradiation, there's no reaction. So let me just quote a saying by Professor Jeff Ozon, who is widely considered the father of nanochemistry and also the university professor in the University of Toronto. And to him, the problem for photocatalysis right now is not materials, because we have a lot of highly active and selective materials already out there. Rather, it's a photocatalyst and photoreactor optochemical engineering challenge. And as I mentioned, I used a tool called optofluidics, and just also around 10 years ago, my PhD advisor, Derek Erickson, while he was doing a postdoc with Dimitri Sautis and Caltech, his original focus was microfluidics for point-of-care diagnostics, and later they figured out there's a way to use the same principle to enable not only the point-of-care diagnostics efficiency, but also can unlock new opportunities for energy applications. In my specific example, I've been going to talk about, that's going to focus on photocatalysis, but I want to mention that as long as the reaction involves interaction of light, fluids, and sometimes also heat, there's a potential to apply this platform technology to design new reactant devices for innovations. So to give you a snapshot about what I achieved from the project without going into any of the details, on the left-hand side, you can see the reactor prototype that I developed, which is 0.1 liter prototype in a basement lab of Ithaca, New York, where I did my PhD at Cornell. And in 2021, the project was upscaled and field tested in Gillette, Wyoming, was one of the 10 finalist teams in the 20 million carbon X prize competition. And in that competition, only 10 teams were selected to enter the final level, and we focus on conversion of CO2 into different products, including fuels and feedstocks, which is the things we focus on. There are also other teams who focus on CO2 conversion to plastics, nanotube, and polymers and other sustainable products. So to give you an overview about what this design involves and how it is related to surface and structural engineering. So basically, this is the reactor design, and it consists of two components. The first component is to do optical control. And the goal here is that if you don't do the optical control, if you look at the light shining from the a side flange window, and since there's no optical control, light is gonna experience exponential decay. So with a finite distance of the light transmission, light is gone, and that means, photon is gone. That means the photocatalytic reaction cannot happen. And the goal here is to see whether we can use the waveguides, which is the routes we show here, to distribute the photons in a better configuration, so that the full number of the photons is still the same if you look at the area beneath both of the configurations. It's just how we distribute the photons in a scalable configuration. And at the same time, when you have the kinds of material, you have the photons, you also need to have the reactant to be delivered to the desired location. And in this case, I pretty much borrowed the concept of a shear and tube heat exchanger to borrow the baffle design to deliver the reactants to the desired location. This is just one of the early iterations of the technologies. But pretty much the goal is to use optical control to deliver photons, and then fluid control to enable the precision delivery of the reactant to the catalyst surface. And what is inside these early configurations for the reactor is that if you shine light from the side, and then there is the optical waveguides inside the reactor to make sure the optical control and fluid control can be achieved simultaneously. And in order to showcase the performance of the reactor, we want to use established reactions to prove the performance and compare with the state of art. And remember, this reactor is a platform technology. The reason we choose this CO2 plus hydrogen to form carbon monoxide and water, which is a reverse water gas reaction, is because we want to compare with the literature. But having said that, the reactor can also work for any other photo-driven processes, for example, ammonia production and also water splitting, presumably. So about the waveguides optical control, firstly, we want to understand how to change the surface morphology. And the key parameter we are looking at here is the attenuation coefficient. That means how fast, how rapidly the photons will just, the intensity will decrease over the transmission line. And after, there are a couple of methods to change the surface morphology and surface properties that lead to the change of attenuation coefficient, either by physical method or by chemical method. And the method I presented here is based on just chemical agent, pretty straightforward. And firstly, you want to understand how the attenuation coefficient will change versus the agent time. And then we want to understand, in order to achieve a linear, more or less uniform distribution of the photons, what is the relationship between attenuation coefficient with the distance and different locations of the waveguides, so that we understand for each distance, each location, what is the surface property we want to apply to that specific location. And there are, as I mentioned, there are several methods to achieve this, either by just creating the cracks by physical methods, or you can also do a variety of chemical processes such as etching and controlled rate at different locations of the waveguides. And if you still recall the example I illustrated earlier, the previous distribution will be the gradient decay of the photons intensity. And after the gradient A-chain method of the waveguides, we achieved a more or less uniform distribution of the photons along a longer and scalable configuration along a line of distribution. So the principle behind this is that if you look at the surface property, we instead of having a very uniform surface properties where that will lead to exponential decay, we change. We applied a gradient distribution of the surface roughness so that when it's further away from the light transmission, the photons emitted from the transmission are still more or less similar. And if you look at numbers, which is the coefficient of variation, which is an indicator of the light distribution uniformity, after our gradient H-chain, we achieved much better uniformity of light distribution. And also regarding the fluid control, there are apparently microfluidic methods to achieve this, but we also want to scale up this technology for the field deployment. So we ended up using the configuration of different baffles to study the influence on the fluid field. And what is showing here is a couple of the helical baffles. We also study the different plate baffle, what is the opening number, spacing, how will that affect the fluid delivery. At the same time, we use multiphysics modeling to analyze and optimize the design and operating parameters so that we had maximized fluid flow, heat transfer, and reacting yield at the same time. So let's look at the reactor. Again, this is one of the early lab prototypes that we tested in laboratory conditions. And we want to compare with the literature. So we use the exact same material, exact the same operation condition, like flow rates, operating temperature, pressure, light source, intensity, and we just want to keep everything consistent so that we can be fair in our comparison with the literature. So as you see here, the product formation rate and quantum yield versus the literature on the same conditions, we achieve more than 25 times increase for both of this. And what is more exciting is that beyond the early lab scale prototype, we also tested the potential for diameter scale up so that we can have a higher throughput for the reactor. And also, in the same time, you wouldn't want to scale up a reactor to 100 or 1,000 liter forever. This is the middle point we reached. We come out with the volume, the throughput of the reactor that we are comfortable to work with, and then we put reactors operating parallel and test. And so the goal here is to increase the throughput without just building a crazy big reactor. And because of the design of the surface of the waveguides and also the reactor components inside this specific reactor, in 2017, this design that led by me achieved one of the I think it was actually one of the over 1,000 entries we achieved the grand prize. We were the grand prize winner internationally, and also I landed on several other recognition because of the implications of this work. And what is more exciting is that what I already showed here, this is the pilot project we tested in Wyoming. And because this is a competition, so all this efficiency, all the conversion rate need to be verified by third party. So in this specific application in Wyoming pilot, the only energy input into the system is solar, and the is being tested next to a coal-burning power plant. And the third-party verified efficiency of CO2 to syngas, which is a mixture of hydrogen and carbon monoxide, the conversion rate is over 50% over a couple of weeks during the competition. So that's what is more exciting beyond just the lab prototype. And also because of the performance in a pilot project, most recently in 2 years ago, there's a United Airlines contract that purchases 300 million gallons of sustainable aviation fuels over the next 20 years. Because in the first step, you can make syngas, which is hydrogen and carbon monoxide from CO2, and also in a later processing from syngas as the input of the system, there's a Fischer-Tropsch process pretty established in the industry that you can convert syngas into longer chain hydrocarbons, which potentially can use to produce the aviation fuels. And also just in 2023, there's 20 million Series A raised for this spin-off company from my PhD effort. So which is pretty exciting. But I think what is more exciting is that the recognition and also especially from one of the few experts that Professor Ozen says this is compartmentalized, self-contained, and modular units can potentially make CO2 catalysis to see the light of the day. So I've spent a lot of time discussing this project, and the key takeaway here is that by doing surface engineering of the waveguides and also the structure engineering, you can achieve the simultaneous and precision control of the light and fluids, leading to enhanced reaction rate. And also this is potentially expandable to other processes that involve interaction of light, heat, and fluids. So this is about the first project. Now I wanted to talk briefly about a second project, which still uses surface and structure engineering, but for a different application, which is for the particular matter PM capture. So the rationale for doing this is that right now we spend around 80% of our lives in an indoor setting. So the indoor pollution control has gained significance and immediacy. And for larger size particular matter, such as 100 micrometer in diameter, it takes around 4 to 9 hours to float and to reach the ground. But if you think about 1 micrometer in diameter particular matter, it's going to take much longer, which is 19 to 98 days. So that means there's a huge danger compared to a larger size. So the very fine size, millimeter size PM, especially below 1 millimeter, there's a lot of challenge and also a lot of need to remove that. And currently, when we think about using the fiber membranes, which is established method to do that, is oftentimes the trade-off between the efficiency and also the resistance. Because in order to make sure you have very high efficiency, sometimes you have to compact the fibers really densely so that you reduce the gap. But at the same time, if you do that, this forces the air resistance to increase significantly. And as I mentioned, this is a trade-off we are facing. And this is one of the other people's work to illustrate that. For example, if the throughput is 32 liter per minute, and for this specific particle size, the efficiency is around 36%. And if you increase the airflow rate, that will decrease because of the increased air resistance here. And the key summary of this work is that I designed the electrostatic responsive fiber membrane so that I achieve a very high filtration efficiency, which is around 98%. At the same time, also with reduced air resistance. And this was done by surface modification to the membranes. So this is the membrane we're talking about here. And if you think, there are 2 takeaways I want to mention here. Firstly, we end up using the silk nanofiber to do the modification for the surfaces for the membrane. And secondly, the rationale for doing that is that there are 2 components inside silk nanofiber. There's the hot components, which you can use that to improve the mechanical property that we care about. And at the same time, there's a soft segments which provide a very huge free volume so that we can enhance the dielectric property at the same time. So by utilizing the silk nanofiber modification for the surface of the membrane, we achieve both enhanced mechanical property and also enhanced dielectric property. And this work was recently published on Device of Cell Press. And if you look at the mechanical property enhancement, let's look at figure D here, which shows the stress strain correlation. And as you see here, if we without any of the modification and 0%, very small amount of the stress, which you see here, that can cause the strain to by more than 40%, and which is not good. And also, if you look at figure E here, which is a compression strength and modulus curves. And here, the key takeaway is that there's optimal concentration we want to modify to change the surface property. And this is the setup. I wouldn't go into the details, which is to test the efficiency for the PM filtration. And here I wanted to quickly compare two data points, which is at 0%, which is no modification, and 2%, which is 2% modification by doping nanofiber by silk into the membrane surface. And if you compare the direct filtration, and that is 0 and around 1.3% for 0% no modification, and when you move to 2% modification, there's 9% ish of efficiency. If you change that from direct filtration to electrostatic drive, that efficiency for both of these have a huge increase. And for the 2% here compared to the other percentage of doping, we achieved around 99%, 0.7% of the filtration efficiency. And then here is the figure to show the optimal air resistance for the different doping. And by combining the efficiency and the air resistance, which is our optimization goal, we define a quality factor so that if you have a high quality factor, that means you have a very low air resistance and a very high clean efficiency. And for all of the doping efficiency here, we see and 2% is the optimal level. Again, this is to show the long-term performance and the effect of the air velocity and concentration on the filtration efficiency. And here is to show, after 400 hours operation, it still maintain a pretty constant level of efficiency of the removal. And this is the principle and rationale we come behind. We do COMSOL modeling to compare both of the configurations, and we see after modification there is around 14.5 increase in system capacitance. That leads to the increased efficiency. And finally, just want to mention, this is a quick summary of this work. And the principle here have a lot of implications for other fields, for example, petroleum engineering. And in my talk, I talk about the surface structure engineering to lead to efficient devices for carbon management and particulate matter removal. But these are just one of the few examples that we can potentially leverage surface structure engineering principles to lead to efficient devices that can work in the field. So finally, just want to thank my collaborator, especially my PhD advisor, David Rexon and Cornell, and also my mentors from the Schmidt Science Fellowship, and also my collaborators at MIT. So thanks so much. I'm happy to take questions. I know I'm running out of time. Apologies. Happy to take questions.
Okay, thank you very much, Doctor, for your interesting talk. So, do you have any questions from the audience? Okay, it's a very nice talk. In your first part, you focused on the reactor of CO2 conversions. So I'm wondering if this reactor can be used for hydrogen production.
Yeah, so I would say this is definitely possible because this is the platform technology. If the reaction pathway you are using involve interaction of light fluids and heat, I think presumably you can adapt that reactor for the other settings. And also there are definitely some nuances you need to change because the reaction I'm using is gas phase reaction for CO2 catalysis, but I have already shown using the same principle, I can adapt that for example, other applications like wastewater photocatalysis driven process as well. So definitely there's a lot of research already happening for hydrogen production from photocatalysis. So definitely I think there's a lot of potential to do that.
Okay, thank you. Is there any more questions? Okay, so I have another quick question also about the first part of your presentation. So I'm wondering, so you optimize the service to make the annotation coefficient more uniform. So I'm wondering, did you also optimize the distribution or something like for the CO2 catalysis along the height of the tube?
Yeah, that's a very good question. So in order to make things work, you need to have the light fluids, which is CO2, and also the catalyst material to be existing in the same place at the same time. So in this specific configuration, it's a fixed bed reactor. We already coat the catalyst materials on the surface of the waveguides, so that the reason we want to have uniform distribution is that we already have uniform distribution of the catalyst materials there already. But having said that, if you change a reactor from a fixed bed configuration to, let's say, a fluidized bed reactor, so in that specific application, there are a couple of ways to also achieve that. So in that case, I wouldn't think we still use the rod-like waveguides. We can potentially use the something like a glass bead like waveguides, so that we can serve as scattering sites for the light distribution when the catalyst material is fully fluidized and our light is also fluidized, to make sure where there's catalyst material, there's the reactant delivery, there's also the light delivery. So the principle here is that it doesn't have to be waveguide like shape. We just want to use a principle to design configurations of the reactor to have the concurrent delivery of light and fluids to the catalyst surface. Whether it's a fixed bed or the flat bed, we can design different configurations.
Okay, thank you. So if there's no more questions, I think and we will thank Dr. again, and we will move on. Thank you.
All right. Thanks so much. All right. Take care. Bye-bye.